Hello everybody, this is Dr. Bricker here with Chapter 21, Part 2, Calculating the Electrical Potential. So last time we looked at what you can do with the electrical potential, and in this video we'll look at how we actually can calculate it. So from last time, if you remember, the use of the electrical potential, or in other words voltage, was if you knew the voltage at a certain spot, just multiply it by the amount of charge that you're trying to put there, and you can come up with the amount of energy that it would take to put the charge there, and that would be how much energy you've stored there. And then you can use that energy for a variety of potential applications, for example, accelerating different charges. So here we're going to, in this video, figure out how to actually calculate the potential. Now that we know what to do with it, how do you go back a step maybe and calculate it? So electrical potential inside a parallel plate capacitor. So if you remember what a capacitor is, let me actually draw this out. Oops. A capacitor is a separation of charge. So we had something like one plate over here, another plate over here. This one we can make positively charged, this plate negatively charged, and then we have an electric field that goes across. So if you put a charged particle between the plates of a parallel plate capacitor, if it's a positive charge, it will accelerate to the right. There'll be a force on it this way. Negative charge would do the opposite. So that's sort of complicated to look at in terms of electric field, because an electric field is a vector quantity. So hopefully we can come up with the voltage inside of a parallel plate capacitor, and we will, and then we'll be able to figure out how much energy is stored there. Okay, so that's what a parallel plate capacitor is. Here's a better picture of it actually. So in this picture, positive over here, negative over there. Electric field goes across this direction. If you try to take this charge here and move it to the other side, you have to put a force on it. It doesn't want to go there. And you can figure out how much the force is from F is equal to Q times E. So we have a force through a distance. That's what work actually is, going back to physics 220. Okay, so the amount of work that you do is equal to the amount of energy that is stored in that position. Okay, just like loading up a spring, for example. Okay, so we'll build on this idea to come up with the idea of voltage in just a second. So for a parallel plate capacitor, you're free to choose whatever point is 0. So we're going to choose, reference point of the negative plate. So everything is relative to the negative plate. Just like with gravity, we just chose the ground to be 0 potential energy. We can do the same thing here. The negative plate is 0 electrical potential energy. Okay, and then we can, based on that, figure out how much work we have to do as we try to move the charge across. So as we try to move the charge, going back a slide, from this position over to, I'll just call this position 1 to position 2, we're putting a force on the charge. Through a distance, we can figure out how much work we have. And again, that's equal to the amount of energy that we've stored there. Okay? Okay, so this is what you saw before. F is equal to really the magnitude of the charge times E. And then the work, force times distance, turns out to be QEX. So the amount of electrical energy that we've stored is equal to the work, force times distance, or we could write it as QEX. Okay? So, this is what you saw from the last slide. Now, if you divide this whole thing by Q, so divide this by Q, you got to divide everything by Q. If you divide by Q, these Q's actually cancel out, and we're left with energy per charge. That's what the voltage actually is. So energy per charge is E times X. Good. So this is the voltage. This is the electric field times X. So we've come up with the voltage, or electrical potential, in other words, of a parallel plate capacitor. And then if you remember from the previous chapter, the electric field due to a parallel plate capacitor is this. This is the electric field due to a parallel plate capacitor. So we could plug that in. And finally, then we have what the voltage for a parallel plate capacitor is. Qx over epsilon naught, that's just the constant, times A. Okay? So the voltage across the capacitor turns out to just be E times D then, if you go all the way across the capacitor. This is the voltage at some location. So when x is equal to 0, the voltage is equal to 0. When you go all the way across, x is equal to D, and that's where this is coming from. Okay? So it's uniformly spaced. As you step across the capacitor, say it's 10 volts across the capacitor. Right in the middle would be 5 then, right, when you're halfway across. Okay, excellent. And here's how the electric field is related to the voltage across the capacitor. Just doing a little bit of algebra there. Okay, very good. So we've got our first potential that we could actually calculate, our first voltage that we could calculate. Okay, very good. Usually we talk about the voltage across the capacitor, not the voltage, at some point in between the capacitor, but this is the way to actually solve that then. So if the distance across is, say, 10 centimeters and you're halfway across, so x is equal to 5 centimeters, the voltage would be half the voltage across. So it's nice and evenly spaced all the way across, as you can see from this picture. Negative plate, 0 voltage. In this example, the voltage across is 1.5. So when you're a third of the way, you're at 0.5, 2/3 of the way, 1, all the way 1.5. Here's a side view of this. Okay, good. Now here's a graph of voltage versus position as well. So I come back to capacitors a lot because it's a situation where you have a constant uniform electric field. We saw that in Physics 220 for constant uniform gravitational field. So it's nice to go back to what we've seen before. That's why capacitors keep coming up. Okay, good. And there's a better picture of the voltage across the capacitor. Okay, same thing here. This is a bigger view of what we've just talked about. Okay, these are not actual plates or anything like that. This is just a plane, like imaginary plane. 1/3 of the way across, you have anywhere in there 0.5, 2/3 anywhere on that plane. There's not literally something there. It's just space. Okay. And then here's the side view, going from one plate to the next. Now in reality, here's I drew the electric field lines going right across like that. We're just looking at the area right between the plates. In reality, when you start to get off to the side, the electric field lines do something like that. We do a lab where you actually, when we were in person, measure the voltage and construct the electric field lines. And even with our equipment, you would get something that looks like this. So, excuse me. So the green dashed lines are equipotential surfaces. This is where the voltage is all the same. So here, the voltage is all the same. Here, the voltage is all the same. In the topographical map analogy, this is going at the same elevation. So if you took a charge and you try to move a charge anywhere along the dotted green line, it wouldn't take any work at all because you're not going up or down. You're staying at the same surface. Now to go from 1 volt to, say, 0.5 volts or something like that, there would be a change in voltage. Okay, so here's an example. A parallel plate capacitor is constructed of 2 discs spaced 2 millimeters apart. Okay, good. It is charged to a potential difference of 500 volts. Okay, excellent. A proton is shot. Okay, so a proton. Right away we know the charge of a proton. So this is the fundamental charge. 1.6 to the minus 19th coulombs. So whenever you see electron proton, you know the magnitude of the charge. Okay, proton shot through a small hole in the negative plate, heads towards the positive plate. We know that this has to be the negative plate because that's 0 volts. This is 500 volts. Okay, so a positive charge shot through there doesn't want to go to the positive plate, so it starts slowing down. So the electric field is slowing it down, as you can see from the picture there. We want to know what is the farthest distance from the negative plate that a proton reaches. So it comes in with some energy, some kinetic energy, because it's moving. And as it goes into the capacitor, it slows down. So all of that kinetic energy that we have is turned into electrical potential energy. Okay, good. So we want to figure out what's the farthest distance. Okay, so we're doing kinetic energy turning into electrical potential energy. Okay, that's a synopsis of what I've said. And again, it's a proton, so we actually know the mass of a proton too. Okay, so the proton starts at the negative plate where x is equal to 0. Let's find the final point. So the final point is when all of the kinetic energy, so there is none left, final velocity of 0, turns into electrical potential energy. Okay, so be careful. This is a big V, this is a little v. Okay, and that's some more information that we know. Okay, so here's energy conservation. This is the initial energy. Sorry, that's the final energy. This is kinetic plus electrical potential, final. This is kinetic plus electrical potential, initial, right? Because charge times voltage, that's energy. That's what this is. U final. That's what this is. U initial. Okay, so when it stops, there is no kinetic. When you first enter the capacitor, there is no electrical potential. So those are actually 0. Okay, and this term is charge times voltage, right? That's the amount of voltage that we'll have at that spot from the formula that we just saw. This is the initial kinetic energy. Do some math, put all the numbers together, and this proton would go in here 0.84 millimeters. Okay, good. And again, the mass here, you can look it up. This is the mass of a proton. Something like 1.673 to the minus 27th kilograms. All right, excellent. So you can stop a proton. So 0.84 millimeters, less than halfway across before stopping. So it would stop, and then it would turn around and go back the other direction. Okay, so here's a nice synopsis of parallel plate capacitors. We saw this in the previous chapter, the first part here, the electric field. Q epsilon naught over A. Sometimes we could write this one actually as surface charge, like charge per area, divided by epsilon naught. So we did that in the previous chapter. Now we have a way of looking at it in terms of voltage too. Good. Excellent. So this is a nice slide with a summary of what's going on here. So I will make a separate video talking about your second homework set. Okay, so the electrical potential energy of 2-point charges. Here's the formula for it. So if you've got a couple of charges, there's potential energy between them. So let's do it like this. Here's charge Q. It's just sitting here. You can put it there for free. Let me erase this. And now you want to bring charge Q prime in. So we're moving charge Q prime here. Q prime may or may not want to be by charge Q. So there's an amount of electrical potential energy between them. Say they both are positively charged or both negatively charged. And there's nothing around. You could easily bring Q there. Just bring Q there. There's nothing to stop you from doing that. If you try to bring a like charge, Q prime, close to Q, they don't like to be by each other, so you store energy between them. And here's the formula for the energy between charges. It's a dot. This is supposed to be a dot too. And this is the distance between them, R. Okay, so K, that's the constant that we had before. Q prime divided by the distance between them. No absolute values on Q or Q prime, and the R is not squared here. Let me say one thing. This is K, the constant. 8.99 times 10 to the 9th. Newton meters squared over Coulomb squared. In the previous example, the K that you saw was kinetic energy. That's why with kinetic energy, this previous example, almost always write this as Ke. That's the kinetic energy K. This, in this current slide, that's the constant K. So you can see why it's confusing. K. Okay. So if we know the voltages, we could write this in terms of the potential because of a point charge then. Because remember, voltage is the energy divided by the charge. Here's the formula for the energy between charges. You see it there. So take that and divide it by Q prime, and you come up with this. This is the voltage because of a point charge. Voltage, K, Q over R. So we had the voltage associated with the capacitor. Here's the voltage if you just have a charge sitting there. Okay? So we've got a couple of scenarios where we can calculate it. Now if you have more than one charge with voltage, you just can add them up. We'll see that, I think, in a subsequent slide. First though, here's a positive charge. These are three different ways of looking at it. So when you're really close to this positive charge, you can see what the equipotential surfaces look like. Remember, it's K, Q over R. So if you're twice as far away, the voltage is half as much. Okay? Graphically, it would look like this. It just goes, the voltage is proportional to 1 over R. Okay. So again, with this, I will make a separate homework video. All right, excellent. So the electrical potential inside a charged sphere, so if you have some kind of charged sphere, it's the same as the electrical potential on the outside of a point charge. Okay, so we have something like this. So you can figure out the voltage at the surface, and then going farther if you have an actual charged sphere. So something like this. You can figure out the voltage out here, some distance away. That's what R is here. R is not the radius of the sphere. R is this distance. And then the potential at the surface, or if you go into the surface, it stays the same. There's no potential difference inside the sphere. Okay, so you can pretend the charged sphere is just like a point charge. That's what the Q is, the charge on the sphere. Okay, excellent. So there's the formula again. Now if you have a whole bunch of point charges, you just add up the voltage contribution. So that's what this means, add them all up. So add up all the K, Q over R's. So if you have, say, 3 point charges, you would just add up the voltage at that spot. So for example, if you had a charge here, let me just call this one like Q1, and then you had over here Q2, and you wanted to figure out the voltage at this spot. I'm just picking a random spot. This distance would be R1. This distance would be R2, and then the total voltage would be just add those up. So this would be K Q1 over R1 plus K Q2 divided by R2. And there could be more. I mean, this is just, I'm just giving an example of this formula. The nice thing is, there's no, it's not a vector. You don't have to look at different directions. I mean, I could even figure out, whoops, the voltage at that spot because of, like, I'll just put another one here, Q3. Q3 is located there. I'll just call this distance R3, and then I can do K, Q3, R3. And that's at some strange angle, but in terms of voltage, you just add them together. That's the power of this. It's not a vector. Okay, so here's a positive and negative charge, and kind of like what I started to do here with just a couple of charges, Q1 and Q2. This is an electric dipole, and you want to look at the voltage because of an electric dipole. Say, let's do the V is equal to 0 line. You can pick this point, for example. So the voltage at that point is due to the positive charge and the negative charge. They're the same distance away, So as long as you were the same distance away, one is positive, one's negative, they add up to 0 because they have the same charge. Opposite signs, though. Okay, and then again, I will make a separate homework video for that. So there's a connection between electrical potential and field. So the electrical potential, or in other words, voltage, and electric field are not two distinct entities, but they are just looking at the problem from different perspectives. Electric field's a vector, the electrical potential is a scalar. It's just different ways of looking at the same thing. So one way might be easier to solve a problem, or maybe the other way is easier to solve a problem. Okay, so the electric field lines are always perpendicular to these equipotential surfaces. Why is that true? Well, if they weren't, say, this is wrong, but say that the electric field was this direction, not perpendicular, then you would have part of the electric field this way and part of the electric field that way. This part of the electric field would actually make the charge experience a force and slow down, speed up, but it's not, because it's an equipotential surface. You can move something around for free there. So electric field lines always have to be perpendicular. If not, we would not be at the same potential. Okay? Okay, so the electric field lines also point in the direction of decreasing potential. So you go from a higher voltage to a lower voltage. And that makes sense too if you think about this about a positive charge. If you put it here, it's going to accelerate. Oh, it's supposed to be positive. It would have to have a force this way, right, from higher potential to lower potential. So the electric field lines have to point in that direction as well, from higher to lower. Okay, so connecting potential and field, we kind of already saw this. The work is the change in the amount of electrical potential energy. That's equal to Q delta V. This is the new part, really, of this chapter. But the work is also the force times the distance. That's from Physics 220. The force is Q times E. That's from chapter 20. So we can put all this together. So if the work is this and the work is this, you can set those equal to each other. And then the electric field is delta V divided by D. Okay, so there is a mathematical connection between them as well. And points from higher to lower voltage. Okay, good. That's kind of a picture that goes along with what we just did. All right, excellent. So if you want to go from lower to higher, that's what's going on here. I'm just going to pick some numbers. 0 volts, 10 volts. So to do this, you have to actually put a force on a positive charge, right? It doesn't want to go from 0 to 10 volts. That's like going uphill to this charge. So we'd have to do some work. Okay, and again, the electric field's always perpendicular to the potential lines, the equipotential surfaces. Here's a couple of pictures. Here's a point charge. So if you remember, the electric field, because of a point charge, was K Q over R squared, and it points away. The voltage we just saw is K Q over R. Okay, so that's for a point charge. Dipole is a little more complicated. Definitely doable, but more complicated. And here's the electric field and voltage because of a parallel plate capacitor. We just went through those formulas. Okay, good. So really, the separation of charge here, I mean, again, I can't really stress it enough. You're watching this video based on things that you can't see. I'm sure there's a capacitor involved somewhere with what you're doing right now. And it all comes back to the fundamental force idea that positive and negative charges are attracted to each other, likes repel. It all comes back to that simple idea. One of the 4 fundamental force laws. Okay, and then again I'll make a homework video on this. What are the magnitude and direction of the electric field at the dot? Okay, so let's take a look at this. This is 200 volts here, 100 volts, 0 volts. Okay, so I know the electric field has to point this direction. And I know the magnitude of it is delta V over D. Okay, so let's go all the way across this thing to figure this out. So the electric field, the difference in voltage from the right side all the way to the left side would be 200 volts divided by the distance between this whole thing, 2 centimeters, so 0.02 meters. And you can calculate the potential that way. Okay, and that would just be some number. So we've got 2 times 10 to the 10th, and this would be 2 times 10 to the minus 2, right? That's what the bottom is. I'm just rewriting this formula up there. So this turns out to be 1 times 10 to the 4th then. Okay, so you can do that one without using your calculator. Volts per meter. Okay, so volts per meter, that's the electric field strength. Turns out that's the same thing as a Newton per Coulomb. So why is that? Maybe if I can free up some room here, we can take a look at it. A volt is a joule per coulomb. I'm going to write it down here actually. So I'm showing you that a volt per meter is the same thing as a Newton per Coulomb. A volt is a joule per coulomb. So I'm taking this and writing it down here. So volt is a joule per coulomb, and I still have a meter left. Now a joule is a Newton times a meter, and then I still have a coulomb and meter here. So the meters cancel out. So a volt per meter is the same thing as a Newton per Coulomb. Okay, just so you realize that, same units. Okay, good. So again, we'll take a look at 21.82 later. So a conductor in electrostatic equilibrium. Charges are not moving around. All excess charges on the surface, if it weren't on the surface, then there would be an electric field inside, and there's not because we're in electrostatic equilibrium. The electric field is 0 inside. Same thing, if it weren't 0, charges would be moving around, and they're not by definition. The exterior electric field is perpendicular to the surface. It would have to be if a part of the electric field were not perpendicular to the surface, charges would be moving around. And again, see the title here. And the electric field is sharpest at the corners. That's because that's where charge accumulates. Okay, and the conductor is at the same same potential. If it weren't, then you have a potential difference and charges would be moving around. See the title again. Okay, soon we'll have a situation where charges are moving around. We'll have current flowing. Not yet, though. Okay, so inside a conductor, the electric field is 0, therefore no work can be done on a charge, and you could easily move it around. There's no voltage. Charges could easily have moved around. But excess charges, though, are on the surface, just like this picture shows. Okay. Capacitance and capacitors. So it's formed by 2 conductors with equal but opposite charges, as you know. Sometimes they're called electrodes or plates. They could be squares, circles. Sometimes we make spheric or cylindrical capacitors. But we haven't talked about those yet. We've seen pictures of them, but we haven't talked about them. So it can be used to store charge. If they store charge, they store energy. That's one use. They're also used in other sorts of circuits for different reasons. Okay, so in a capacitor, the electric field strength is proportional to the voltage across. And the potential difference increases as the charge increases. So the more and more charge you put on, the bigger and bigger the potential difference is. Okay, that's what I meant to say. Yeah, E and delta V are proportional to the amount of charge. Okay. Something like this. So this picture, there's more charge. The electric field's bigger. The voltage across the capacitor is bigger. Now remember, if you put on too much charge, you can have a spark go across. So we're not talking about that happening. So the charge is proportional to the voltage, and I could write it like this: charge proportional to the voltage that we have across. And there's a constant that relates these to each other. So this is just proportional to. The constant that relates charge to voltage is called the capacitance. Be careful, this is capacitance, a variable. It's measured in farads. We also have charge that's measured in coulombs, so it can become confusing. Charge measured in coulombs, which is a C. This C that you see here, where the arrow is pointing to, is the capacitance measured in farads. So charge per volt, that's what a farad is. You know, coulomb per volt, I should say. So it's the constant of proportionality between charge and voltage. It turns out it just depends on some physical parameters of the capacitor. Basically the area and the distance between the plates. So shape, size, spacing of the two electrodes. Large capacitance can store more charge, and then electric field could be larger. So to charge a capacitor, you need to move charge from one plate to the next. And the easiest way to do this is with the battery. So you can charge up the plates. Now, and then you have charge there. The difference between a capacitor and a battery is through chemical processes, the battery maintains a voltage across it. A capacitor, you charge it up and then you use it, and then you got to recharge it somehow. So a capacitor is kind of like a single-use battery in a way. And you can do it kind of like this. If you hook up the negative plate of a battery, or sorry, the negative side of a battery and the positive side, you can have a situation like this happen. Electrons that are free to move from this plate move to the positive side of the battery, making this side positively charged. And on the other side, electrons here are free to leave, and then they come over here. So in this way, you actually charge up the capacitor. So the picture is kind of showing like positive charges moving through the wire and ending up over here. That's not really what's happening. Negative charges leaving this plate and moving this direction, leaving the plate positively charged. So the negative charges are what actually move around. Okay, so when this thing is completely charged, the potential of the battery is equal to the potential of the capacitor across the capacitor. Okay, and that's how you can actually charge it up. If you remove the battery, now you have a potential difference. You've stored charge and you could use it for something else. And again, we will come back to that one. In this example, though, we have a 1.3 microfarad. Okay, so that just the units show you that that is the capacitance of the capacitor connected to this battery. What is the charge on the capacitor? Okay, so we know the voltage, we know the capacitance, we now have the relationship between capacitance, voltage, and charge. This relationship. So Q would be C times delta V. We're assuming that it's completely charged. So multiply those together, and you end up with a amount of charge, 2 times 10 to the minus 6th. So a farad is a coulomb per volt, remember. Coulomb per volt. These are units. This is a variable. Okay. Good, so the positive plate has 2 to the minus 6th, the negative plate has negative 2 to the minus 6th. Okay, so here's a nice synopsis of everything we have. Not everything, but a lot of to do with the capacitor. Electric field is equal to this. What this slide is going to do is come up with the actual equation for the capacitor based on characteristics of the capacitor. So this is the electric field. We see here. Remember, this is also the electric field. This is from chapter 20. We can set those equal to each other. Solve for Q. So take this, solve for Q. Q is equal to something times the voltage. The something here is the capacitance. That's what C has to be, right? That's what we set up before. Q was proportional to the voltage across the capacitor. And what set those equal was the constant of proportionality called the capacitance. So whatever comes in front of delta V sub C here has to be the capacitance, and that's what this is. Okay, so area of a plate divided by the distance between the capacitor. That's the capacitance. And you can see it here. So bigger area leads to bigger capacitance. Smaller separation leads to bigger capacitance. Okay, so the capacitance is, from what we just saw, epsilon naught A over D. Okay, epsilon naught, reminding you, is that constant 8.85 to the minus 12 Newton meters squared per Coulomb squared. The area is going to be the area of one of the plates. So parallel plate capacitor, 1 meter on a side. So the area, 1 times 1 will give us 1. Now the separation between the plates is also given. It's 1 millimeter. So be careful. This would have to be 1 to the minus 3rd meters. Good. So to solve for the capacitance, you can put this in. We have everything here. We have epsilon naught's a constant. The plates, nice and easy to calculate, 1 meter on each side. The separation between the plates is this. So you can put this in to get the capacitance. And then we know Q is equal to C times the voltage across the capacitor. So they're saying, okay, now that you got C from the first part, if the voltage across the capacitor is 100 volts, how much is the charge? So we, again, you have the voltage across it. It's given in the problem. Capacitance we got from the first part, multiply those together to get the amount of charge. Okay, very good. One more part with capacitors are energy and capacitance. So what we're looking at with capacitors in this, for our purposes, is how much energy is stored in the capacitor. Okay, so the amount of energy that the capacitor stored is Q times delta V. Really, this comes from what we did earlier in the chapter. Energy per charge will give us the voltage. So if you solved for the amount of energy, it would be V times Q. Well, the Q here is the energy on just one of the plates, and the delta V then is the voltage across the capacitor on average, right? Because the voltage changes as you go across. So to get the average, just take the voltage across and divide it by 2. That would give you the average voltage. So that's where the 1/2 is coming from in the formula. Okay, it really comes from the fact that when you start with the capacitor, the first charge you move from one plate to the next is for free. There's nothing stopping you from doing it. And then when you build up more and more charge, it's harder and harder to do it. So on average, we can look at how much energy is stored using the average voltage. That's kind of the idea behind the 1/2. And then there's a lot of other ways of writing this. I mean, probably you start with this. U is equal to 1/2 Q delta V across the capacitor. But then don't forget Q is equal to C times delta V across the capacitor. So you could take this for Q and plug it in here, eliminate Q that way. If we do that, you get this formula. You could also, from the formula, eliminate delta V by solving for delta V in this formula and plugging it in. So there's 3 different ways of writing it. Here are 2 of them, and then here's the 3rd one. So 1/2 Q delta V, or 1/2 Q squared over C, or 1/2 C times delta V squared. Okay, it all comes from this idea though. So 3 different ways of writing the energy stored in a capacitor. Okay, so a capacitor bank used to power a large electromagnet is charged to 23,500 volts and stores 8.4 megajoules of energy. What is the total capacitance? Okay, so let's write down what we know. The voltage across the capacitance, I'm going to write it like this. 2.35 times 10 to the 4th volts. The energy stored in the capacitor, 8.4 times 10 to the 6th joules. We want to know the capacitance. Okay, so let's go back to the previous slide. We have voltage and energy. We want the capacitance. Okay, so So here's energy and voltage. We're looking for the capacitance. So energy is 1/2 C delta V squared. C delta V across the capacitor squared. Okay, and then the only thing that we don't know in the formula is the C. So this would be 2 energy in capacitor. I'm multiplying both sides by 2 divided by delta V across the capacitor squared. That would give me the capacitance. Okay, and then we have everything again. Here's the energy, megajoules. Here's the voltage. Okay, so put everything in. Don't forget the 1/2 factor in this formula, and you can come up with the capacitance. Okay, so charge per volt it'll turn out to be. Okay, very nice. So a capacitor can charge very slowly and then release the energy very quickly. Here's an application, defibrillator. So fibrillation is a state in which the heart muscle twitch and cannot pump blood. The defibrillator is a large capacitor that can store 360 joules of energy and release it very quickly, 2 milliseconds. So you probably have seen this on TV, charging, clear, put the pads down, release energy really quickly, 2 milliseconds. And then you have to charge it up again if you have to use the paddles again. Okay, very good. So the rest of the slides are just a summary. Again, the first part of the chapter is this sort of thing. What's the use of voltage? Getting things to maybe accelerate. And then what we did today was looking at how you can actually produce different scenarios of having voltage. Okay, I'll make the homework video and talk to you soon.